All right, so this is going to be the video that helps to explain the solution that I posted about previously. Gets me a 3 millisecond runtime sometimes. It's pretty quick. This is going to be the solution to 2945, find maximum non-decreasing array length. So I'll explain the question and then explain the solution. You're given a zero-indexed integer array nums. You can perform any number of operations where each operation involves selecting a subarray of the array and replacing it with the sum of its elements. For example, if the given array is 1, 3, 5, 6, and you select subarray 3, 5, the array will convert to 1, 8, 6. Return the maximum length of a non-decreasing array that can be made after applying operations. A subarray is a continuous, non-empty sequence of elements within an array. So they give a couple examples. 522, they combine the whole thing into a 9 to get 1, and that's a non-decreasing subarray. Excuse me, non-decreasing array. 1, 2, 3, 4 is already non-decreasing, so answer is 4. Right? That's the largest you could do. And 4326 can become 456, which is of size 3. Important is to note a few things. This is a particularly tough question with a low acceptance rate and not even that many submissions, and of the submissions, a very small number. So less than a fifth of the answers are correct when they're submitted. Also, the numbers are going to be, it's going to be up to 100,000, so quite a large array of numbers, relatively speaking. And all the numbers are positive and non-zero, which is also significant. That's important. Okay, so let me discuss the solution that I had come up with in the interest of time. This is a very interesting question, though, but it should, once you ponder it for a bit, you realize this is a tough question. It's definitely one of the tough ones. So I took this test case because I thought it was instructive. And let me go ahead and explain a couple of things before I start describing this test case and how I could illustrate the solution that I came up with. So prefix of j is a useful construct, and this is going to be the sum from 0 to j exclusive on j, or understood another way, it's the sum of the first j elements, which is very useful in this particular case. And then if you take the difference between prefix of j and prefix of I, you end up with the sum over I to j exclusive on j, which is also helpful, which basically would be the sum of first j elements minus the first I elements. Right, that's probably the easiest way to think about it. It's going to be this, by the way, this sum from I to j, this is zero indexed. Easiest way to think about it would be this becomes the sum between those two sets, meaning it's the first j element summed together minus the first I element summed together, or the first j element summed minus the first I elements. Okay, that's a useful construct, and if you notice here, there's some optimizations I did, but I built it here, and it's very simple. You just take the next element and add it to the previous sum and set that to your position at that spot. Okay, now for this particular test case, I can illustrate the solution and try to explain what's going on. In simple terms, we want to have a non-decreasing sequence, and we want the longest sequence. Okay, and what we're going to want to do is for each grouping of elements that we sum, we're going to want to find the smallest grouping of elements, subarray group, that we can, that's going to be greater than or equal to that previous subarray in the subarray sum in the sequence. And we're not necessarily going to use a pure greedy algorithm. because it actually doesn't quite work. So this is a good example where it doesn't work. So if we tried to just go straight through, we said, okay, start with this element is larger, these two elements are larger than that one, the next elements that are larger than that one extend all the way to 884, and you end up with an issue because these two are not going to be large enough to cover 884 and 305, right? You can see that quickly, that the 80 here, if you moved it over to the 385, you have two numbers here that are larger than these two numbers. You can pair them off and show that. So that means that this whole thing would have to be combined into one giant number, and you'd end up with 1, 2, 3. So the third grouping is here, and the fourth one at the end, which is not optimal. 4 is good, but it's not the optimal. Interestingly, the optimal solution actually groups here. So 418, 730, then groups here for the fourth grouping, and then groups here for the fifth grouping. And the way this is found is the way that this algorithm is going to work to find this. What we're going to do is we're going to say, okay, take the first element, first, I guess, one set of size 1 elements, and then try to figure out how many elements we need to be larger. So it's just 1 in this case. And then now, for every consideration afterwards, we're going to assume we've got an optimal solution that stops at this point. And then we're going to add, for all of those other solutions, we're going to add a 1 and say, okay, we got one subset, we've got one subarray there already. And it's guaranteed, as soon as we found one of these subarray groupings, let's say if it was here, that subarray grouping, it's larger than the previous subarray sum. That means that every other one that's larger is also guaranteed to be larger, right? And so we can reuse that same left bound on not just considering these two elements, but considering these ones and these ones and these ones. And actually, the way the algorithm is set up, it considers it elements of size 1, 1 element, 2 elements, 3 elements, 4 elements, 5 elements, etc. It goes one by one, increasing the set of considered elements each time. So when we consider element 2, and we say, okay, look at these two elements, we've got the left bound, we're going to split this now on this left bound and just consider this element, and we're going to look for what is larger than that element. It's going to be these two together. This leads us down that path that I described before, which is sort of the greedier version, which basically puts us at a grouping of 1, 2, 3, and 4, which is suboptimal. However, if we consider now 3 elements, we can say, well, we already had this sub array of 1. We're now going to consider these 2 elements, which we know are already going to be larger than this one because it's already been guaranteed that this one's larger, right? So we can propagate that left bound across to this point. And we say, okay, let's find something larger than these 2. Well, the one that's larger than these 2 is going to be these 3. And then we can, over here, set the left bound exactly at this point. And we say, okay, these 3 elements now are accounted for. These 3 elements are now what we're looking at, we're trying to account for. And it looks like this is going to be the solution at that point, the partial solution at that point. And then now, once we're considering all of these elements, we can say, right, we can set our left bound here. We say this is all accounted for already. And now that we're looking at this section, 1, 2, 3, 4, 5, 6, 7, 8 elements, it looks like, then we want something larger. It's going to be this subarray. That's going to be larger than these 2. As I mentioned, having the rest of this already accounted for. And by the way, in between, we're going to do things like, well, consider this point here and say, well, this is all accounted for already here. How about from here to here, when is there going to be a value that's larger than this one? It does get a bit peculiar. I want to say there is something here that's interesting. What about this element? What happens here when we consider this one? Well, right. So it's at this point that this is accounted for. At this point, however, it's probably just going to be here, I think, that's accounted for. Yes. Yeah, it's a little bit involved if you get a little bit deeper into the subtleties there. But that's the basic idea. Oh, and that's kind of hard to explain in 10 minutes. Going over time a little bit, but that's okay. This may be a 15-minute video. So I'll try to walk through the code now with that explanation. So as I mentioned, we're going to go through the number of elements. We're going to have this boundary that I'll come back to explain what that is. And we're going to have our propagating furthest left bound, as I mentioned. We're going to use the prefix array to set up the target, which is going to be, target is going to be something like prefix of j minus prefix of I is going to be greater than or equal to prefix of I minus prefix of L, where L is the left side, which gives us the target is going to be prefix of j, and that has got to be greater than or equal to 2 times the prefix of I minus prefix of left, right? We're going to add this prefix of I to both sides. And that's why I have this target here, prefix. And there's a tiny optimization to multiply bit shift instead of multiplying by 2. These parts are a very clever optimization we'll come back to. As I mentioned, we're going to DP on the elements. It's going to be once a new section has been found, we're going to add that to the previous DP up to that point. We just add 1. So you're going to say DP of that element section that we've now identified another segment ahead. And we're going to say, okay, our solution for this number of elements that we're considering is going to be the left portion that were found, however that many segments there are, plus 1. Basically meaning that this new section that we just considered has been added. And then, as I mentioned, we're going to update to the end of the sum that's going to be the next sum in the sequence. That element is going to have a left bound backwards to where we're at right now in elements. So when you get to that point, you're going to consider, okay, this left bound tells me, this left bound will tell me how many elements I've already accounted for, right? So it's sort of they call a forward DP. Right. Now, this part is very significant. This actually is not that hard to grasp or understand. There's 2 big optimizations here that push this over into the very fast category from fast to very fast. Because we're using prefix arrays, you could figure out what this boundary is by using a binary search, because these values are going to be non-decreasing. The prefix array is non-decreasing. Note that we actually are looking for a target in the prefix array itself. So we're looking for the j coordinate, j index, for which this holds, right? That's what the target is going to be this. I actually did this wrong. Target is this part. We're looking for the index or the boundary, test bound, for which that condition holds, that the prefix of the test bound is greater than or equal to that target. So You could use a binary search and do it in logarithmic time, and that's not too hard to do. But a much cleverer approach is to, instead of using a binary search, you notice that the right side boundaries are very similar across iterations to each other. They're only off by a few iterations. There are a few, plus or minus a few values. And so a more efficient approach is to assume that that's the case. And instead, if you're too far to the right, we're going to move back, right? That's what this loop does. Pretty simple. And if you're not far enough to the right, you're going to move to the right. So if you're too far to the right, you're going to move back to the left. And if you're not far enough, you're going to move to the right. And this is coded in such a way where you're basically always, if you iterate once here, then you're guaranteed to iterate at least once down here. And then you'll be in the right spot. And so that's very efficient. That's extremely efficient. It becomes effectively O of n time instead of O of n times log n, you get basically O of n time. And also a big optimization, huge optimization here that really makes things fast is because there are only 100,000 elements, and because there's going to almost guaranteed to be at least one test case that has 100,000 elements, it's perfectly fine to statically allocate this memory. And between all of the test cases, that memory will always be there. You don't need to constantly reallocate memory. And then all you've got to do is just overwrite the memory that you're working with between calls. And so that's a big optimization too. And using raw arrays is slightly more efficient than using other possible array types. So I basically just overwrite the part of the array that I'm going to use at each iteration. This is also subtle. This is just kind of an artifact of how I've set things up. These slight modifications of the +2, +1, that has to do with putting a 0 in front of the prefix array makes it a little bit longer. And then there's also the way these loops are set up. Being able to access the last element without causing issues kind of makes a difference. And then it's best to, again, how it's programmed, it's a little bit easier to just copy the final result twice at the end. And there's a subtlety here that's significant. So it's just typically would be considered like a code smell because it's not using a standard algorithm. I think you could use standard transform here potentially, but it was a little bit easier for me to think about this with a raw loop. The important thing here is casting the incoming num values, because they're integers, to long longs so that the sums will fit in the prefix array is significant. And doing this all in one loop is also good, as opposed to using like various algorithm kind of manipulations to kind of get this to work. There's probably a way to do this that is a little more standard, but I opted for this because it was a little bit easier for me to think about. So there you go. That's my solution. And unfortunately, I am 18 minutes over. Not as I wish this video was shorter, but there you go. That's my solution. It's relatively quick. And thank you for watching. There you go. 100%, 100%. Not bad.